Hi kids, thanks for watching this third video in this unit. The topic is momentum, and the essential question is, what are the relationships that contribute to the momentum of moving objects? So momentum is a word that probably most of you guys have heard or used before in conversation. In general, all moving objects have momentum, and we'll learn about the definition in a minute or two. But the variable is p. It's a capital P for no good reason. This is the first time we have this like random variable. Of course, we don't want to use an m because we've already used m, which is probably why they picked something different like capital P. The units of momentum are kilogram meter per second, which is kind of ugly, but there's no shortcut. There's no way of making that easier. You'll see where those units come from when we come up with the equation in just a few minutes. So if I ask you guys to give me an example of an object with a large momenta is plural for momentum, objects like a football player probably come to mind, right? A pretty big object, and they move pretty fast. Maybe bigger than that, something like a train has more momentum than that football player even, because it's bigger and faster. And even bigger than that, a comet, hopefully not spelling the end of life as we know it on Earth, but a big comet has a huge mass and a huge velocity, so it's got a lot of momentum. On the other end of the spectrum, we've got things that still have momentum, but a very small amount of momentum. That little guy riding his tricycle, not nearly as much as the three objects in the row above. Hamster running on a wheel. That wheel would have some momentum because it's moving. It's actually a slightly different kind of momentum because it's spinning instead of moving sideways, but we'll go with it for now. Less momentum, of course, than the boy because it's smaller and not moving as fast. And a really small amount of momentum, that P. Of course, if it's just sitting on the table, it actually has no momentum. So an object that's not moving has no momentum at all. So based on what we already know about momentum, what are the variables that are going to come into our momentum equation? What are the variables that are going to have relationships with momentum? Hopefully you guys would have guessed that mass, m, has a relationship with momentum, because the bigger the mass, the bigger the momentum. That means there is a linear relationship between momentum and mass. The other variable that impacts momentum is the velocity, or v. And as you probably would just logically guess, the bigger the velocity, the bigger the momentum too. So there's a second linear relationship between momentum and velocity. So given those two relationships that we just talked about, we should be able to figure out or derive an equation for momentum. Remember that the variable p, which is momentum, has a linear relationship with mass and a linear relationship with velocity. Please take a second before you look forward in this video, pause it, and try to figure out what the equation for p is. Hopefully you stop the video and you're back and you figured this out. P is equal to mv. In that equation, you can see there's no inverse relationships, nothing on the denominator of that equation, but two linear relationships. If you look at the units of p, which I told you earlier, it should make more sense now because the units of mass are kilogram and the units of velocity are meters per second. So the units of p, momentum, have to be kilograms times meters per second because that's what's happening in that equation. I want to talk quickly about some trends or misconceptions that commonly arise with momentum. The first is that you can have positive and negative momentum. The sign of momentum is going to depend on the direction of motion, or the sign of the velocity. So any object that has a positive velocity, so it's moving forwards, is going to have a positive momentum. And any object that has negative velocity, so it's moving in whatever direction you decide is backwards, is going to also have a negative momentum. Negative doesn't mean less momentum than positive. You can have a train that's moving at negative 10,000 meters per second, and that thing's going to have a heck of a lot of momentum compared to, and a heck of a lot of negative momentum compared to a tiny mouse that might be walking in the positive direction, which would have a very small amount of momentum. It just happens to be in the positive direction. A second trend and misconception that I think pops up every now and again is that you should realize that mass and velocity both impact momentum equally. So there's lots of ways to get big momentum. Either positive, either a lot of mass or a lot of velocity, or both could give us a lot of momentum. So if I look at kind of a scale here from large momentum to no momentum down at the far end, you'll notice that, you know, a big mass and a big velocity give us a lot of momentum. Sort of medium momentums can be reached a lot of different ways. I could have a sort of a medium amount of each. I could have a lot of velocity but a very small amount of mass, or a lot of mass and a small velocity. And objects that have a very small amount of momentum usually have a small amount of mass and velocity. Of course, lots of objects have no momentum. Any object that has a velocity of 0 is going to have no momentum, whether or not they're a huge boulder or tanker ship or something. If they're stopped, if they have no velocity, they also have no momentum. So let's summarize. Take a minute, please, and go back to that essential question. What are the relationships that contribute to the momentum of moving objects? And once you've thought about that, I really would love for you to take a few minutes to fill out the graphic organizer or the extension questions to help you be really prepared for class. Thank you.